So, one of my subscribers sent me a whole bunch of questions, which is awesome because that is like the hardest part for me, is finding questions in a timely manner that makes the stream kind of boring. They kind of like took cell phone pictures of them on the laptop, which I think is funny. People do this all the time, and it's just like, just take a screenshot. But I'll take it however I can get it, honestly. Summer's really slow for me, so this is perfect. And basically, I'm just gonna work through all these problems, and hopefully they will be able to join the live stream at some point, and ask questions like with the problem that I'm on, because I don't know if I'm under explaining things, over explaining things. Honestly, I don't know if anyone can even hear me because I don't really check the audio to see if it's working. So yeah, there's all that. But hopefully somebody finds this useful, and the subscriber who sent me this, please share it with your classmates, because that would be cool. And then maybe they'll subscribe. And right now I have 42 subscribers, so I feel pretty good about that. All right, so in the regular hexagon shown, okay, that's a hexagon, hex meaning 6. Write a single vector that is equivalent to each expression. A single vector that is equivalent to each expression. Oh, I see. Okay. That's super weird. So AB plus BC. This is a really bizarre way of like asking this question. I think I understand what they mean. So let's just like highlight these as we go. So this is AB. And then this is BC. So if you're adding these line segments, the vector sum of these things, the like resultant vector, would be to here. So that would be AC, if that makes sense. I really don't like how they phrase this, but let's say this is AC. I don't like the notation either. I've got a big problem with the notation. This is AC. This is how I would denote that, with an arrow. Yeah, anyway, let's keep going. Let's not dwell on that. So then, same sort of thing. Okay, somebody's watching. I don't know who that is. Hopefully it's the person whose homework this is. Say hello in the chat if you can. AC minus BC. Okay, so the way that you add vectors graphically is like tip to tail. So if we were adding this one to this one, it would be like that. That's how we did the last one, and then you would just, the resultant would be from the tail of the first to the tip of the other one. But then subtracting this vector would mean like, okay, so actually I can do this in a new layer. So let's add a layer, and then I'll do like a slightly different colored vector here. I actually have to do this because I'm like, I have to actually draw this out because I'm terrible at drawing these. So from B to C would be like this direction here, but since we're subtracting it, we want the negative. Okay, so rather than thinking about what it means to subtract vectors, just make the negative of that vector and then add them. So I'm going to take this guy and we're just going to move it like that. And so this would be the resultant vector. This doesn't make any sense. So this would be the vector. I really don't know, right? A single vector that is equivalent to each expression. Maybe they mean draw a vector. Anyway, the vector that we would be looking for here is, I'll make it kind of blue, would be from here to here. And then you would draw a little guy on this. And we can't really name that as one of the other vectors on the hexagon. Yeah. So I guess this blue one would be the answer here. Let's call it V. V. Sorry if this is hard to read. And actually, real quick, I kind of have an audience of one here. So what I want to do is just go back to Reddit, and I'm gonna see if that person said anything in. Okay, well, in Reddit chat. Say hello in the YouTube chat. Okay, so when they show up, they'll be a minor celebrity. If anyone couldn't tell, that was a joke. Okay, so then we've got EF plus BC, and you probably already figured this out. I'm sure most of you guys will be way faster than me at this, since I am not fast. I'm going to turn this off, since we don't need that anymore. And you guys feel free to like draw this as neatly, as messily as you want on your thing. I definitely am going to have a hard time with this, so sorry I didn't make enough layers. Okay, here we go. So that's back, and then we put a layer on top of this, so this will be our next problem. And we are here, so we've got EF, which is going to be here. Oops. And then it's from E to F, then BC. So then we've got one from B to C, and I'm even going to do another layer of this, so it's easy to see. From B to C. And the tip will be here. And I said that you add these tip to tail. So you'll see how this will look whenever you add it like this. And from basically the start of the green one to the end of the green one here to the arrow end on the purple one is the vector, which is like the null vector. Which, you're going to have your own notation for that. It's the null vector. Actually, let's see what... I suspect that this is going to be very different notation than what I'm used to, because the definitions that this class has used so far are very different. So, boom, boom, boom. I'm just Googling. What is the common notation for this? I guess it's just called 0. Let's call it 0. Okay, so we'll call you 0. And then I'm going to turn these two layers off since we don't need that for D. And then, so EA, we add a layer here. So from E to A is this vector, and then we'll just put the tip of this arrow here, and then I'll make another layer, and then FB, so from F to B, and oh, actually we want minus FB, so I'll just do the negative of that, which is BF, essentially, and then EC. Okay, EC. So basically what I'm doing is I'm first like drawing the vectors, and then I'm going to add them all by kind of like writing them tip to tail. So we just need to add these up, and it's actually commutative. Oh, I probably should do another layer so I can really move this around. From E to C. Okay. And then Okay, so then we'll go here and add this. Oops, we'll add this one like so. And then we'll go here and we'll move this one. Come on now. Oh, that's really interesting. So these guys are like the negative of each other. So when we add them out, or when we add them together, we just get EA. So this is actually just equal to EA, which is pretty cool, actually. That works. So this might confuse some people that negative FB, let me change the color so you can see this. Negative FB is actually BF. And then EC. It doesn't make sense that vector addition works this way because you're really thinking of these things as an array when you first get them, like a partial line, like a line that only goes forever in one direction. But that's actually not what they are. These have length. They don't go forever in one direction. They have a certain length, and they also have a direction. That's why we draw the tip here. This is kind of why I don't really like doing this graphically. I think it actually makes it harder to understand. The better way to do it would be to actually like write out, vector notation, like 1, 2, and add these things like in vector notation. It makes so much more sense that way. I think that's probably what this class is building to. Let's see if, the rest of these problems go that way. So I'm going to just get rid of all of that since we're done with those. Oh, okay. So I got a response from our person who posted the questions in Reddit, but they may not be able to hear us yet. Somebody's watching. Hello, whoever's watching, say hi if you can. Okay, so let's go back to our questions. So I'm going to go to the next problem 2 now. Find the magnitude and direction of the resultant. Use one method for B and a different method for C. Okay, I can't really see here. Let me see if... Okay, this is... Oh, okay, so here's number 2 and okay, so these are kind of out of order. I'm going to just do these in the order that they're on the file that I got. It doesn't really matter. All right, here comes another question. Normally when I'm tutoring, I use like Google Meets so we can both draw on it. I can draw like a little bit more interesting pictures on this thing, so that's kind of nice, but it's also a lot more clunky. Is the following a vector or a scalar? Okay, today's date. So vectors need 2 things. They need magnitude and they need direction. So magnitude is like another name for, or like synonymous with like size or scale. And then scalar, you can actually see the word scale. It's just scale. It only has size. So I would say today's date is just like a number. If you want to think of it that way, I would call that a scalar. This is a scalar. It doesn't have a direction. A train traveling at 80 miles per hour. So this is kind of a misleading question. Because you have 2 things here. Like a train is neither a vector nor a scalar. Like that doesn't make any sense whatsoever. So what they're referring to is they're talking about this 80 kilometers per hour. So there's 2 kind of ideas here: speed and velocity. Velocity is a vector. Velocity is your speed combined with the direction that you're going. So if this said like a train traveling at 80 kilometers east, I would call that velocity. But here, just 80 kilometers per hour, that's speed. That's a scalar. And these questions are kind of bad, so I'm assuming that the teacher made this up. So what I would do is I would write scalar, and then if they give you any points off or something like that, just argue with them. Teachers love that. The force of gravity. So force is always a vector. Force is a vector. Why? Because you have this direction that the force is acting on. It has a scale, right? You can measure it, like weight is weight is the force of gravity, right? So how much something weighs, it can be measured at the scale, literally, and then it always has the direction of like the two bodies coming together, or in the case of like us, since we have this inertial frame of reference of the planet, it's like towards the center of gravity of the planet. So this is definitely a vector quantity. Force is always a vector quantity. The temperature outside, scalar, no direction. So it has scale, but it has no direction, or magnitude, but no direction. So that's what you need. For vector, you have to have both. For scalar, you just need scale. Okay, so let's call that, and then why don't I actually just add a layer here while I'm thinking of it. And I want to pull up the chat just so I can see if anyone says anything. Okay, nobody said anything. Really, like the only time people there, I had one very participative person in the chat, and then another time my niece popped in and she talked a lot, which was really cool. Okay, so draw the following vectors using the scale 1 centimeter equals 50 kilometers per hour. Okay. On your diagram, include the measurement of each vector. So I would say probably like stressing about how accurate your angles are is the wrong way to go here. You should care as little as possible. Care like exactly as much as your teachers do, which is probably not very much. So I'll make myself some axes if I can ever figure out why this thing doesn't love me. Okay, there we go. And then we'll go like this. Okay, so this is X, this is Y. I can definitely do some quadratic graphs. I actually have like a bunch of problems for this person that I'm doing now. Let me see. So I've got these 5 that are on the screen, and it looks like I've got 5 more beyond that. So I could squeeze yours in. Do you want to, do you have Imgur? I actually don't know how to pronounce that. Imgur? Sorry. I don't know, like, if you're up to, like, the current moment in the thing. Can you post your questions on Imgur and link it to me? And my name's Ryan, by the way. I'm not actually Glauxy. Glauxy is the channel. Okay. Yeah, I can definitely help you. Or are we connected on Reddit at all? Because you can also just send it to me in a chat on there too. Yeah. I'll just type. Is it a particular question, or do you need it from the top? No, form from, like. Yeah, so we'll get everybody in there. I have nothing better to do, honestly. Just studying. All right, let me do this page and then we'll... Oh, tippity top. Okay, that's okay. Yeah, if you have a study guide, so if you have a study guide, so let's try and get these done since we got these questions in first. But yeah, I'm not going to leave you hanging. We can do it. Boom, boom, boom. And, you know, if you share the link with your classmates, that will help them, but it will also really help me because I would love it if more people would come to the channel. Someday I'd like to get paid for this, but I doubt it. All right, so draw the following vectors using the scale 1 centimeter. This is ridiculous. So you have to like actually break out a ruler to do this. I think that's kind of silly. Maybe even you would want to just have a protractor that has one like end of it a ruler. But we can try to like, I'll help you figure out the scale here. So on your diagram, include measurement of each vector in centimeters. Okay, we'll just like write what it is in centimeters. So we want to do 200 kilometers per hour. And we want it to be at at 20 degrees. Now, usually when you're talking about this kind of thing, this is like compass bearing, which we would call this 0, and it like goes in that direction. So like north is 0, and then you kind of no. She just linked YouTube videos. Okay. No worries. Okay, so what we're going to do is we'll just do the 20 degrees first. So 20 degrees from north is going to be, I don't know, you'll want to measure this, but so halfway is 45, so this is like 30, so we'll call that 20, right? So yours should look something approximately like that. This angle is 20 degrees, and use your protractor. Now, we want to convert 200 kilometers per hour using this scale here. So we need to cancel kilometers per hour and get centimeters. So what I want to do is I want to start by like making a conversion factor. So this is our identity here. We start by writing that down. And I've got kilometers per hour sort of like in the numerator here. So I'm going to divide both sides of my identity by 50 kilometers per hour. 50 kilometers per hour. Ugh. Sorry about the handwriting here. So 50 kilometers per hour divided by 50 kilometers per hour is equal to 1. That means this conversion factor is equal to 1. And when something is equal to 1, you can multiply by that willy-nilly. Like you don't need to consider anything at all. You just multiply by that. So this is 1 centimeter divided by 50 kilometers per hour. And so we multiply by that, and then that's how we get our conversion factor. So these cancel with these, and then you can cancel a 10 out of both of these. 20 divided by 5 is 4. So 4 times 1 times centimeters is 4 centimeters. Now, the way that this thing works is you just treat these units of measure as if they're factors in a multiplication. You just treat it like it's 2 or 7, and you can cancel them just like that. So that's called unit analysis. It's a really handy skill. For the rest of these problems, I'm going to multiply by 1 over 50, and we will skip the discussion for that. But for this first one, it's 4 centimeters. So we don't have a scale set up for this thing. At home, you'll use your ruler. But let's just say this is 4 centimeters. So I'll draw my vector. Oh, sorry, I guess I should not use red. I like to use red because it contrasts with black really nicely, and also to kind of desensitize people to that. So this, we'll just write 4 centimeters somewhere near the tip of, usually label vectors near the tip of them. I like to desensitize people to the red so that when they get red on their paper, they don't get dejected. Okay, so I'm going to erase this work. Also, you can always like come back to this, so don't stress about it. Boom, 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 boom. Hey, Colton, thank you for the questions. Hopefully these answers are like helping you. Okay, so then so that was A. For 2B, what we're gonna do is the same thing. I just want to like take this 75 kilometers per hour and multiply it by that conversion factor, which we created in the last problem, 1 over 50. And then, so this is like 3 times 25, and this is 2 times 25. So I've got 3 halves, centimeters, which is the same as 1.5. So we'll call that 1.5 centimeters, which is probably how your teacher wants to see it anyway. and it's at 10 degrees, so it's actually inside of this. Let's change the color for this vector here. So I want it to be halfway between this angle and north, since that one's 20 and the one we're trying to make is 10. So I'll put it like in between them. I want to also have a sense of scale here. So that's like 2, since it's about half the length, and a little bit less than that, it'll be 1.5. You will actually, measure this, since you're a good student and I'm not that great of a student. Okay. And then, if you can fit 10 degrees in there, try, but somewhere on here you should write 1.5 centimeters. And using them to check my work. I have 2 more for later. Not pages, just 2 questions. Okay, yeah. Throw those. Just do the same thing you did before, and we'll get to them. I am going to stick in some quadratic stuff in the middle of this possibly, but we'll get to all yours. No, you're a good student. Like, you're being proactive and you're like seeking out help. That's a really good thing to do. And I'm glad I can help you. You're helping me too. Like, you're watching my channel and stuff. So that's really cool. All right, let's do the next one. We can make it blue. And so this is 2C now. And so we're going to do the same thing. The only thing we have to do is figure out the conversion from kilometers per hour to centimeter. So we're going to multiply it by that 1/50 and just scroll back to see how we make this conversion factor. So there's 50 here, or actually let's cancel it a little bit. So we'll do 10, all right? And then I have 35 divided by 5, which is 7. So this is 7 centimeters. And I'm being lazy. I'm not redoing all that centimeter stuff, but you should write all that out. Yeah, I'm really glad to help, Colton. I know studying math by yourself is kind of a bummer, and COVID has really messed everybody up. Okay, so southeast. So south is this way, and it's like never eat soggy waffles, which is just like, probably good advice, but it's a little boring. So southeast is halfway between south and east. So it's like kind of like what would be negative 45 degrees here if you were using the measurements that you use on the unit circle, which are way more sensical. And then we want this thing to be 7 centimeters. So this guy is 4, so like, longer than that. You'll be measuring this out with your ruler, hopefully. So but if you write 7 centimeters, then what are they going to do? Fight you? Yeah. So this is question 2. Yeah, that's a huge bummer. Definitely send your classmates this, especially if they have the exact same questions. I think, I'm looking at the screenshot that you sent, and it looks like this is coming from a website. So, what is... Oh, I see. Question 2 comes up in the next thing. Yeah, if this is like on MathLab or one of those kind of websites, they may not have the exact same questions, but hopefully my, explanations help a little bit. And, if they jump in, they can ask their own questions too. So it doesn't have to all be on you. Okay, so let's do... So I'm just going to... Oh, actually, why don't I just leave this and make a new layer, just in case you had a question on it. Pull it back up. Okay, boom. Here's a new layer. All right, so we're on number 3 now. And I would say, Colton, like, stay with the current question in case you have any live... Okay, it's a school. Oh, so do you enter the answers on the website, or do you write it on paper and, like, submit it that way? And then just, like, stay with the current question so you can ask questions live. And then if we have to go back later to the first 2, we'll do that. So question 3 says, draw the opposite vector of each vector from question number 2. Okay, so it's a good thing I didn't erase that. Let's bring up number 2. Okay, so the opposite vector is literally the same thing that you think of when you think of the opposite of a number. So if I have a number 2, its opposite is negative 2. It's the number that I would add to it that would make 0. Or in the case of vectors, the vector you'd add to it that makes the 0 vector. Boom, 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 boom. And they want the tail to start at the origin. A thing that your teachers never actually let you know for some reason is that vectors can move around. As long as they have the same direction and magnitude, they are the same vector. That's a really bizarre thing. So there you go. That's the opposite of that one there. If I were doing this and like trying to make myself, have the best homework possible, I would call this A. I would give it a vector symbol. I would call this one negative A and give it a little vector hat there. And then let's do, I guess I'll use the same color I had before. So I'm just going to try and like copy this guy and then move it here. And draw this the best that you can. If you have a protractor, use a protractor. If not, just, try to make it as neat as possible. Use a straight edge, definitely. So then let's label this vector B hat. And be neater than I am. I'm terrible about when you label vectors, you should do it near their tip. So this is B hat. My handwriting is not good either. So this is negative B. Boom, boom, boom. And then, where are we? C. Okay. So let me just use the same color here. And the same process. This is a big bummer. You may even want to like do these on two different graphs if it's starting to look gross, like mine looks bad. Okay, there. And this is negative C. This is C. Okay, so yeah, opposite means the exact same thing as it does for numbers, because vectors are actually like a generalization of the idea of a number. So the opposite is the thing that you would add to a number. When you add a number and its opposite, you get 0, which is the identity for addition. And the 0 vector is also the identity for vector addition, which is pretty cool. So, okay, that's that. Let's put that baby to bed. You're gone. Bye. And then we'll do 4 now. Boom, boom, boom. So we've got resolve each vector from question 2 into its horizontal and vertical components. Okay, this is dumb. So, yeah, also, I think this is really stupid because they have it in this, like, coordinate system of, like, north being 0. Really don't like that whenever you probably just took trig. But let's do it. So, goodness gracious. I'm going to take these one at a time. So let's go to A. And I'm going to draw a smaller sketch of this so we can see what they mean. So here's our axes, and I'll just redraw this vector a little bit so you can kind of see what we're going for here. All right. So let's say this is 20 degrees and 200 kilometers per hour. Just, imagine with me. If it's not perfectly to the same scale we had before, who cares? When we decompose this thing into its component vectors, what we're doing is, and let me get a different color here, we're breaking it down into these two vectors. So, that's terrible. You got to do a better job than that. So that one, and then say now. Where are we at? That one. And you could probably see, like, if I added these two vectors together, they would, point to that same guy. So these are our component vectors. So the question is, like, how do I find that? Let me show you something here. So I'm going to add a layer, and I'm sorry if this is like tedious watching me draw this. It's kind of hard to do on the computer, but it's probably best that I do as good of a job communicating this as possible. Okay, so here's our vector. This is our x vector. Okay, so it goes in the x direction. And then I'm going to make another layer. I guess you guys can't really see the layers because that's something I'm doing on the side here. I have it like cropped out of the video. Okay, and this is the y component vector in a separate layer, so I can like move these around. So what I'm going to do is I'm just going to like move this x vector. Whoops, not shrink it. I'm going to move this guy here, and you can see that when I do vector addition, right, like tip to tail, it actually points to that vector, and it also makes a right triangle. That's cool. So we know this little angle here is 20 degrees. And these, since they're component vectors, that's 90, which means that this angle here should be 80 degrees. And so we can use our trig relationships to find these out. Okay, so let me take that off just for the sake of it. So if this angle is 20 and I want to know this x vector, I can use the sine. So the sine of 20 degrees is equal to the opposite side, which is actually what we want to know. It's the x. Let's call it x. Actually, let's call it x sub a, since that was a vector. Divided by the hypotenuse, which is actually the full vector. That's the one that we're given. So 200 kilometers per hour, which I'm not going to write that. So to solve for the vector, I'll just have to multiply both sides by 200. 200, and then these cancel. And so I don't know if this like notation is great, but this is the x component of the a vector, which is what I'm going for, is equal to 200 times the sine of 20. Now, you're going to make sure that your calculator is in degree mode, and you're just going to type that in. It's going to give you a number, and it's important to know that this is like 90 degrees from north. It points in the x direction. So when you give this vector, actually, let me grab my dope calculator real quick. I found it. Here we go. So I'm going to make sure I'm in degree mode, and I'm going to type 200 sine of 20. Okay, so it's like 68.4. Let's just round it there. So this is 68.4 kilometers per hour, and it's 90 degrees from north. It's east. You could actually just write east. Okay, so put like a comma or something after the 68.4 and write east. So that's A, or that's not entirely A. We actually need the north vector as well. So to find the other side, we'll use the cosine, right? So this is 20 degrees, and we have the adjacent, and we have the hypotenuse, and so we'll use the cosine. So that's the first part of A. The cosine of 20 degrees is equal to, let's call it like y hat, so it's the y component of vector A, divided by the hypotenuse, which is 200 kilometers per hour. Then we'll do the exact same thing we did on the last one. We'll multiply by 200 on both sides to cancel this guy, and then we get the y component of the a vector, and I'm not committed to that notation, but that's what I'm going to write, is 200 times the cosine of 20, which is 187.9. So it's 187.9 kilometers per hour, and it's due north. So say due north. So yuck. Yeah, I would say that's the answer for A. So let me turn this off, and then we'll do part 3 or 4B now. So this is 4B. And if you don't say anything in the chat, like I'm just gonna keep plowing ahead like you're understanding everything. So we're doing 4B now. Okay, same thing. I'm just gonna like sketch this out so we can see what we're doing. We've got this is 70 degrees. Oh, I want to back up a little bit because I misread this notation. It's south. It's like 75 kilometers south, 10 degrees west, which is just like obnoxious. So you're gonna have to go back, unfortunately, on 2 and redraw this, and then you're gonna have to go back on 3 and redraw the negative. So I'll do both of those for you real quick. So this vector goes south, and then it goes 10 degrees west of that. So it's actually here. And set your scale according to like what you had before. So this is like 75, which it'll have the same thing. I think that we figured that was 1.5 centimeters. So that's actually B. That's the B vector. Then its opposite will be this vector here. So go back and redraw that, what I just drew for question 2. Just erase the B vector that we had done. And then for 3B, this is the opposite vector here. So I'm sorry about that. But let's continue with 4 and like decompose this. It's the exact same process as before. So we've got, this is like the X component. And then the Y component, we can put, let's make her pink. And put it like here. Okay. So the small angle is 10 degrees, and the small thing is like opposite of that. So let's make that the sine. So the sine of 10 degrees. Okay. Is equal to the side we're looking for. Let's call it the x of B over 75 kilometers. Oh, let me just not write the units. And then same thing, I'm going to multiply both sides by 75. And these cancel. So let me punch this into the calculator. 75 sine of 10 is going to be 13. So this is 13 degrees, and it's to the west. Or I'm sorry, 13 kilometers per hour, and it's to the west. So 13 kilometers due west. And that's our first vector. This southern vector, we're going to use the cosine. So we can just kind of like jump directly to this thing. It's the exact same process. Well, let me not be lazy. So we're going to have the cosine of 10 degrees. Okay. Yeah. Actually, why don't Abasi, why don't you like let us know when you get back, and then we'll just take a break from this. We're almost done with this number 5. So once we get done with number 5, I think that would be a natural place to switch, and then we can just talk about what you're doing with quadratics. Okay, so cosine of 10 degrees, that's the small angle here, is going to give the adjacent, which is the vector we're looking for. Let's call it the y of b divided by the hypotenuse, which is actually the vector that they gave us, which is 75. And then we multiply on both sides by 75 to cancel, and we get the y vector of b is equal to 75 times the cosine of 10 degrees. And let's punch that into the calculator. So 75 cosine of 10 gives us 73.9 kilometers, and this is due south. Okay, so let's do the last one for 4 real quick. And this is the 350. So I'm just going to sketch this again. And, I hope, I'm kind of bummed that I made that mistake initially about the south 10 degrees west because I didn't read closely. I just read 10 degrees. But it's good, to see that I do math full time. Like, that's my job. Like, I just do math, and I make mistakes. And the only reason why I caught it was because I drew a little picture. So hopefully that helped you. All right. And then we're going to do southeast now. So south and east. And this is not to the same scale that it was before. This one's the longest vector, 350 degrees. And I'm just drawing this picture so we can see the component vectors. So let's do, I don't know, green and blue. So this one's going to be kind of straightforward since it's, this is like 45 degrees, which we won't even need the calculator for that. So we've got component vectors here. Boom and boom. And so since this is directly southeast, that means this is 45 degrees. So we can do the cosine and the sine of 45 is going to be the same. It's root 2 over 2. So the cosine of 45 is equal to, let's say, the x over the hypotenuse, which is what we're given, 350. So you multiply both sides by 350. And actually, the x and the y are going to be the same. So the x component of c is equal to the y component of c, since the sine and cosine of 45 is the same. Is going to be equal to 350 times the cosine of 45, and that is 350 times root 2 over 2, which everyone knows from their unit circle. If not, I can do a whole thing on that, but maybe tonight wouldn't be the best. So half of 300 is 150, and half of 50 is 25, so this is 175. And so we've got 175 root 2. That's the exact value if you want to put that in as your answer, but let me just type that in the calculator. 75, 247.5. 247.5. Let's say east, due east. And that's kilometers per hour. And then the y, or actually, you know what? I should say like the magnitudes are equal, but these vectors are actually not equal to each other. This is x component of c, and then the y component of c is going to be equal to the same, 247.5 kilometers per hour, but it's south. Due south. Let's say due south. Where can I send it with this? I've already done this. Is actually the only paper I finished today. They give you guys way too much homework. I don't know if you feel, I'm sure you do feel like that, but like they give you way too much homework. I didn't realize it until, I started tutoring, and because I didn't do homework in high school. I couldn't handle it, so I just I had no executive functioning skills, and I have a lot of siblings, so my house was loud, but seeing my students do it, and now my kids just get slammed with homework. There's no reason for it. You didn't learn anything, so yeah. Okay, so a cart is pushed up a ramp with a force of 250 newtons. The ramp sits, okay. So let's draw a picture of this. We've got a horizontal, kind of. There we go, horizontal-ish. And then we have a ramp which sits at a 28-degree angle with the horizontal. So let's draw some ramp. So we'll call that 28, I guess. Come on now. 28-ish. Yeah, my impression is that the reason why they're giving you all this homework is because they just want you to pass the test at all costs. That's the only thing that matters to the school, because that's a lot of their budget and things, and how teachers are assessed comes from passing the exams. So they'll just smash you with homework until you see every question that there is and survive or not. But a major part of this is just like to train you into wanting credit, like you want the points, and that's so you can be a good little worker when you get out of school. Boom, 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 boom. Okay, so the force vector, since they're getting pushed up the ramp, is actually like parallel to the ramp. That's really important. And the magnitude, so it's like the force vector is 28 degrees from the horizontal. The magnitude of the force vector is 250 newtons. Determine. Oh yeah, the like not having exams thing is like really particular to these online COVID changes, and that just absolutely wrecked one of my students. Are you from Canada? Because like the difference in definitions in your material and some of the other like differences in the way you say, like there's no difference between tests and exams for us in the States typically. So you definitely have a Canadian vibe going on. So okay, sorry, I'm chatty. Okay, so we got 28 degrees along the ramp, so our force vector should be parallel to the ramp, and the magnitude is 250 newtons. So this is a vector. It says determine the components of the vector representing the force. So we're going to do the exact same thing that we did before. We're going to take this vector and we're going to break it apart into like a horizontal component and a vertical component. And you can see from like that vertical, if I just move the vertical, which you can totally move vector components, like you can just move vectors around as you want, as long as they are the same direction and the same magnitude, they're the same vector. It doesn't matter where they are. So we can do this, and then this little angle in here is 28 degrees. Okay, so we'll do the exact same thing. We're going to use the cosine for the adjacent, so let's call this the force in the x direction is going to be equal to 250 times the cosine of 28. And a lot of people really want this rule. They want me to say like x is always cosine and y is always sine, but it doesn't work that way if you have like your force vector going like this, and this angle, the cosine is actually y in that case. So you just use the like opposite, use the SOHCAHTOA as we call it. Sine is opposite over the hypotenuse, cosine is adjacent over the hypotenuse, tangent is opposite over adjacent. Just always go off these definitions with force. It'll help you a lot. Yeah, you definitely have the Canada lingo for school. I'm starting to get more and more Canadian students, and your curriculum is really interesting there. It's totally different. And let me just get an approximation for this for you. 250 cosine of 28. So we got 220.1 approximately. Or no, I'm sorry. 220.7. 0.7 newtons. Sorry, my handwriting got a little, why don't I just do this? Newtons. And then the component of the force in the y direction, in this case, is 250 sine of 28. Okay, and we've got 117.4 approximately. And I guess you could say like up, let's say right and up. I don't know. I guess, if you leave these positive, that kind of like is pretty typical notation for to the right in the x direction, and positive is typical for up in the y direction, but it couldn't hurt to say. Describe what would happen if the angle of the ramp is decreased. have no idea what they're asking. So if you decrease the angle of the ramp, the component in the x direction would get bigger, and the component in the y direction would get smaller. Just like assuming that your force vector kind of is always parallel to the ramp. I think that's what they would say. I forgot what I had said, Colton. Do you mean like, how do you have a Canadian vibe? Mostly it's from this the different words. So like in the first problem, I think let me see. Let me find which problem. There was some. So the notation, the vector notation, like I've only seen that in Canadian textbooks, but it's actually all of the ones that I've done so far. They use that vector notation, except for one. And then, resultant. One other vocab. There was some like particular vocab that was different. Vector scalar. I don't know. I think if you go back when you watch it, I commented on which words I was like, oh, that's really weird. But then also in the United States, we don't distinguish between tests and exams. Okay, so for B here, let's just say like if you lower the angle, assuming that the force vector like is always parallel to the angle of the ramp, then the component vector in the x direction will get bigger, and the component in the y direction will get smaller. I think that's what they want you to say for question 5. So let me know if you actually need me to like write that, and I will. So let's pull this. And then I'm going to just like roll into your next question from the blue website. Unless Abasi came back. I'm saying that like kind of in a Persian accent. I don't know if that's the right accent, so like a really trash Persian accent. Okay, cool. So let me roll with 2 then. So find the magnitude and direction of the resultant. Use one method for being a different. What do they mean? The parallelogram method. Components method, aka known as the physics. I have no idea what the parallelogram method is. Oh, I know it. That's so dumb. That's not like a method of vector addition. This is ridiculous. Yeah, okay, so let's use I assume this is like the components method. Let me screenshot this and bring this in so everybody else can see. So dumb. All right, here we go. All right, here's what we're looking at. Find the magnitude and direction of the resultant. So for this problem A, if we just like kind of assume that there's a, like 5 is horizontal and 56 is vertical, then you can draw the resultant here. Let me draw it in red so it kind of stands out. Here's the resultant vector. And you can see when I do that, it makes a right triangle, which is kind of like what everything's going to be based off of. And so we got to figure out first the magnitude, and then we can, once we have that, we can use that to figure out the angles. So, you can see this is a right triangle. We constructed a right triangle. The resultant vector is the hypotenuse. So what we're going to do is we're going to say, let's call this like R for resultant. And I'm going to give it a little vector hat so we know it's a vector. So the magnitude, and sometimes you'll see this with 2 bars, but that's way too much writing, so I'm not going to do that. The magnitude of vector r is going to be the square root of the magnitude of the component vectors squared and then summed. So this is just the Pythagorean theorem. And so what is this going to be? The square root of 25 plus, this is going to be like, what? 2,500 plus 300 plus 300 plus 36. So this will be the square root of 3, 1, 3, 1. You know what? Let me not be a cool guy. Let me just type this in my calculator. 5 squared plus 56 squared. Ah, see, that's why you don't do math in public. 3161. And yeah, how did I get that wrong? Let's take the square root of that. So this is approximately equal to 56.2 meters per second. And now we just have to figure out what direction it's going. So the way that we will do that is I'm gonna, well, I honestly don't know how they will want us to get, so they want us to use the like bearing directions. Okay, that's a major bummer. All right, let's figure out what this angle is here. So we know a bunch of different, we know all of the sides of this triangle, so I can just use the tangent to find this. So the tangent is the opposite over the adjacent. So let's call that little angle there theta, and we'll say that the tangent of theta is equal to the opposite, which is 56, divided by the adjacent, which is 5. And then I need to break theta out of that triangle there. Oh, so you finished all of the ones that I sent you already. Is that what you're saying? Because I don't have to do them if you already have them, especially if you understand them. I think that's the most important thing. Here, let me type in the chat because I think that's actually probably faster. Okay, cool. Yeah, you can post it. Well, here, let me just type it. Okay, cool. So should I finish this one that we're on, or are you good to go with all of these? I just want to make sure we don't like miss any of your questions. I think this is probably like the most watched, well, maybe not the most watched stream, but it's definitely the most like chatted stream for sure. Oh, okay. So I did not get the link. So maybe, yeah, go ahead and send it on Reddit, I think. The other thing I can do is I can just make you a moderator. Okay, you're the moderator now. It should let you do whatever you want. Oh, wait. Did it let you be moderator of the whole channel or just the video? Let me see. Oh, yeah, it made you a moderator for the whole channel. Okay, I took you off the moderator. You are no longer the moderator. Too much power. Let me go to the... Yeah, you can just send it in the chat on Reddit, because I have that open, actually. I have like the analytics for the live stream up in the same window as the chat, and it's got like a chat rate which I have never heard of before. I didn't realize. I want to like the chat rate of the stream at the most recent available time. Let me Google this and see what chat rate means. Okay, cool. I got your Imgur link. Is that how you say it? Imgur? I don't know how to say it. Maybe it's Imager, and it's just supposed to be known. Okay. All right. Some trig stuff. So, given the graph, state the domain, range, x and y intercepts, max and min values and where they occur, period, amplitude, axis of symmetry. And values of A, K, D, and C. Okay, so that's going to be something specific to how you guys do. So I'll have to ask you about that, but that's okay. Where did my mouse go? There we are. Describe two different situations that could be modeled by an exponential function. Okay. Clearly define all variables in the relationship, interpret the growth or decay factor and the initial amount, which cannot be 1. Okay. Function makes sense. Okay, so got it. So I guess we'll do these one at a time. I'm going to delete all of the old question stuff. So hopefully we don't need any of that back. All right. Boom, boom, boom. Okay, so let's do... I thought I got my mouse in this picture. So let's just go and talk about these one by one. Domain and range. So the domain of any like sinusoidal function, like a sine or a cosine, is always all real numbers. So you can say, let me do it like this. So for one, the first one, you would say like the domain is x should be on the interval, or we'll just say all real numbers. You could also say equivalently, this is like the same thing as saying x is on the interval from negative infinity to positive infinity. Because you can put any x value into the sine or the cosine function. We just have to remember domain is the inputs and range is the outputs. Now our outputs is like on the y, so that the highest value we have is here and the lowest value we have is here. That's between 6 and 0. So y is on the interval from 0. It can be equal to 0, so we'll use a square bracket. And it goes as high as 6, which it can be equal to 6. We'll use a square bracket. So that's the first bullet point. And then it wants to know the x and y intercepts. So the x-intercepts, I guess, like, there are a lot of them. you see one that I already highlighted, and then another here. So let's think about how we want to do this. So x-intercepts. The x-intercepts are going to be like at 300, and so this is like 300, 0, right? But you can tell that the function repeats this often. That's the period. So that's like the period here, t, is going to be equal to 300 minus negative 60. So 360. So I don't know if this is degrees or what the x axis is like measured in, but every 360 you're going to get this thing repeating. So all of the x intervals, that's one x interval. You could say this one. You can also, or I'm sorry, x-intercept, and you could also say like negative 60, 0. So these are the two that you can see. If you want to write all of them, every single one, the x value is going to be like 300, and let's say plus 360 times k. And I'll get to that in a second. And then 0. And then you would say like where k is an integer. So you can put any number integer in there for k, and this describes every single x-intercept because there are technically infinitely many of them. Does that make sense to you? Does this like notation here make sense? I don't want to go too much beyond that unless you understand. I think probably this would be sufficient if you describe just those 2 points, but this one is every single, x-intercept, and there are infinitely many of them if this thing is like a sinusoidal. So that's the second bullet. So boom, boom. Okay, yeah, that's kind of hard. Like, I think if you scroll this one back and see how I calculate the period of this thing, you can do like peak to peak or trough to trough. We did trough to trough there. Trough is like the bottom of the wave. And it kind of makes sense. Like, you have one here, and then you do another 360, you'll get another one, and you do another 360, you'll get another one. So the way that I add like a bunch of 360s is with this notation here. So I'm saying like you start at 300 and you add 360 times some number. Now, where am I going to get these numbers? I'm getting them from the integers. So what that means is like, this could be 1. So it'd be like 300 plus 360 times 1. And 300 plus 360 times 2. And you could keep going in the positive direction. This is also like 300 plus 360 times 0, which is just 300 itself, right? And you could also do the negative integers. So like 300 plus 360 times negative 1, which would give you minus 360. So that would go in the negative direction. Minus 2, minus 3, minus 4, and so on. So I see you say you'll do the top part there. What does the top part mean? Like those bullets? You need number 2. Is that what you're saying? Oh, okay. I think I understand what you're saying. You're saying this top part. This is the top part. Unless you mean like all of these. If you mean all of those, I'll skip to 2. So we actually calculated the period. So capital T stands for period, because you're confusing trig students, so you name it with a T. And the way you do that is you can either do this like peak to peak or trough to trough. So we can see 2 troughs, so we'll use those. And you actually saw me calculate this once. You do the later one minus the first one, which we have to do minus negative 60. And that becomes plus 60. So this is 360. So that's the period, is 360. So t is period. And that's here. Oh, I skipped one. The max and the min values. So the max is 6. And that occurs at 126. And the min, we can say, is 0. And that occurs at those same things. So like 300 plus 360k, comma, 0. So that's where the minimums occur, the troughs. Then amplitude. Okay, so the amplitude you figure out by the max minus the min. So we'll do 6 minus 0, which is 6. And this should be like an absolute value. Usually, like this should be positive. So this is the amplitude, 6. The axis of symmetry. I actually don't know what they mean here by. There's an axis of symmetry for parabolas. So axis of symmetry sine function. Oh, they mean the midline. Okay, we call this the midline. Oops. So the way you get the midline, or the axis of symmetry, is you take the average of the peak and the trough, the average of the max and the min. So we'll do 6 plus 0 divided by 2. Let's call this the midline. And this is 6 divided by 2, which is 3. And so if you put the line y equals 3, that is going to give you this line. Which is the axis of symmetry, as they're calling it, or the midline. I don't think there's actually a symmetry in the sense that I'm thinking of it here. So I don't like the term axis of symmetry for that, but that's what they mean. They mean the midline. And then values of A, K, D, and C. Okay, so I need to ask you what this means, A, K, D, and C. Do you have like your base sine formula? Do they give it to you like this, where let me see here. Where are we? It would be like A times the sine of K x plus D plus C. Do they give it to you like that? Because if so, then this is not too hard to do. So if this blue thing is where they're getting those values of A, K, D, and C, just say like that's the formula or something like that. No, that's not how they do it. Okay. I don't know where they're getting these values of A, K, D, and C. That's pretty cool. You can retract a message. And I've never seen that before. Do you know where they're getting those values of A, K, D, and C from? Okay. Yeah, I don't know if I can help with that. I imagine that's what they're actually doing. Let's go under that assumption, because that makes sense. Like, I'm pretty sure what they're doing that. So A is the amplitude. That's 6. This number that we calculated for the amplitude is that, actually. So then C is going to give you the midline. So C is 3. And then inside here, this actually is like K is going to give you the horizontal stretch or shrink. And then D is going to give you your phase shift. So like, let's see. So how do we calculate? I call this omega, but let's use k. So k is going to be equal to 2 pi divided by the normal period, divided by the, let's see, how does this work? So if it's normally 2 pi, we shrink it by a factor of that. Let me just think. So sine function. Bum, 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 bum. Well, I don't want to tell you something wrong. What did they use? BS. Yeah. B was 2 pi. So, and the period is pi. Okay. Yeah, that's what I thought. I just wanted to be sure. So, that k is going to be equal to 2 pi, the normal period, divided by the period that we actually have here. And if you go back, we found our period was 360. So we can just simplify this, cancel a 2 here and a 2 here, and so this is going to be pi over 180. So what do we call that? K is equal to pi over 180. I'm sorry, that explanation is kind of like scant there. Let me know if you have more questions about that. And then, what is the other one? D. So we have kx plus d. What you got to do is you have to actually factor out this k. So this thing is the same as k times x plus d over k. And if you multiply this k back in here, if you distribute that back, you'll see that this is true. But you need to do this in order to actually figure out what d is. And the normal sine function goes through the origin like here and then is above and below. So this point got shifted to the right 30. And so that's what we're trying to figure out here, is what does that make d. So this number should be negative 30. So negative 30, which is a shift to the right, is equal to d over k, but then we found k was pi over 180. So let me just simplify some things here. So negative 30 equals, we're dividing by this thing, so I'll multiply by the reciprocal, so it'll be d times 180 over pi. And then I will cancel that on both sides by multiplying by pi over 180. Pi over 180. So this cancels here. And then d equals, let's see, so there's 60 and negative 1. So this will be negative pi over 60 is d. Okay, sorry. That got to be kind of messy. That is all of number 1. Let me clear this and just start over. And again, if you have any questions on that, just definitely ask, because that last thing was kind of terrible explanation. I'm not doing my best work right now. Describe how this is related to the base function. Okay, so what they're asking here is like, how did we shift? And those numbers that we just found actually help us. So this is shifted to the right 30. So it's shifted right 30. R-I-G-H-T. Woof. It is shifted up 3. And then there's a vertical stretch. Stretch by a factor of oh, I'm sorry. I told you the wrong thing. A is equal to 3. Let me check myself here. So we have to do 6 minus 0 divided by 2. Yeah. A is equal to 3 in this first one. And that's also, no. Hold on, I want to think this through. 0. Up 3, so we go down 3. Nope. It's 6. No, is it? Yeah. I'm sorry. So A is 3, and the amplitude is 3 as well. They should be the same number. I just forgot to divide by 2. Vertical stretch by a factor of 3. And then, where are we going here? And then horizontal stretch. So, this is really interesting. So this is like a horizontal stretch. By, what did I say? Pi over 180. That's where that K comes from. And so that's everything for 2. Now, I don't understand how this language maps to the way so the amplitude is 3, vertical shift up 3, horizontal shift to the right 30. Oh, okay, so you guys, instead of stretch, you say expansion. So everywhere I wrote stretch, you should say expansion. Expansion. And yeah, and there's no reflections. So we're all good with that. Okay. Yeah, I think that's it. And then you posted one more. Let me find it. So, all right, let me know if you're still with me. The second thing here, it says describe 2 different situations that could be used to model. Here, let me just paste it in there. I kind of read this question before we started the other one, and there's stuff that I don't like about this because I think there may be something not included in the screenshot at the very least. One sec. Let me bring this over. Okay, here's that. Boom, 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 boom. Okay, so describe 2 different situations that could be modeled by an exponential function. So one really common application of this for number 1 here is population growth. You saw this over and over and over again. Yeah, I'll just answer it, and then you come back whenever you get a chance and watch it again. So the first application here is population growth. You saw this over and over and over again in the discussion about COVID, as we watched, more and more people get it in the beginning. It was growing exponentially. Then the other way that this work is another way that this would come into play is radioactive decay. So if you have some radioactive substance and you put a bunch of it in the environment, it will decay, meaning the radioactivity So like it'll be in an I'm not a physicist, but anyway, like the amount of the substance will decrease according to an exponential thing. And then it's like clearly define all variables in the relationship. I don't know which relationship they're talking about. So, we could do like A times e to the kt. This might be a thing here. A is the initial amount. It's just a number. E is like approximately 3. It's like 2.7 something. It's a constant. Kind of like pi is a constant. It's a little less than 3. Pi is a little bigger than 3. So this is just a number. Don't get caught up in the fact that that's a letter. It's just a number. K is the growth rate, or growth or decay. And T is time. Interpret the growth or decay factor. So this may be the factor that they're talking about in the initial amount, which cannot be equal to 1. So yeah, there must be some data that they're talking about here. I don't know how we could fit these numbers unless we have data. Interpret the growth or decay factor in the initial amount. A is the initial amount. To fit this, you need data. Like you need to know about the half-life or whatever, or the growth rate. Boom, 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 boom. I have no idea what they're asking for. Should also include reference to at least 2 graphical, numerical, and/or algebraic models. Yeah. Sorry, this question is just like not very good. It's kind of like ill posed. I'm sure somebody else could do a better job at this. But you're welcome. Thanks for the questions. I can see why you're having a hard time in this class because your teacher asks kind of like bad questions. Like there should be data that goes with these questions so we can fit this. And what I really, really recommend, I'll post a link in the chat here, is that you use a pre-calculus textbook, because I think that's kind of like what the equivalent of what we would call the class that you're in now is pre-calculus. And go to this website, openstacks.org. Free textbook there. It's open source. Do what you want with it. And like the highest quality textbooks that I've used, and it's free. So, and they update it constantly. We had another person in the chat. I don't know if they're still here. If there's anybody left, post some questions. Otherwise, I'm going to go back to, well, actually, I might go to bed. It's kind of late. But I'll hang out for a second and just see. Yeah, I don't know. I'll probably watch this again later and see how trashy all of my explanations were. But hopefully we got the job done. I don't know. Let me type this in the chat. Oh man, hour and a half. That took forever. I guess I was probably running my mouth a lot. Okay, well, nobody, I think I always have this like mystery viewer, which like is probably my grandma or something. I have no idea who the mystery viewer is. Maybe it's my girlfriend smirking at me on the couch there. Who knows? But thank you, mystery viewer. Thank you, Colton. Sorry to the other guy or gal or whoever that asked for a question but had to go. Send me questions. Thanks, y'all.